Welcome back to another video. So today we are continuing on with our exponential functions. So we're going to start looking at actually how to model exponential functions in terms of growth and decay. So obviously growth is when our population or area size increases. Decay is obviously when it decreases. So we do have this general formula here. Okay, so we've got P with respect to n is equal to P naught times by a to the power of n. So this is a very basic modeling equation, but one that you will see quite a bit. So P with respect to n is the population. So for our focus, it will be population. Tends to use different letters for different focuses, such as area, you'd use A. But for our case, we're just going to look at population today. So population with respect to n units of time. So this could be hours, weeks, years, centuries, whatever you feel like. P naught is our initial population, okay, so that occurs at the initial moment of looking at our modeling. So typically it's at t equals 0, which is at 0 time. A is the growth factor, so if A is greater than 1, we've got growth. If A is less than 1, we have decay, and n is our unit of time. All right, so we're going to have a look at an example straight away. So the spread of COVID, all right, is something that the whole world has observed and can be modelled within South Australia, where I'm from, by the equation Pn is equal to 1,500 times by 1.25 to the power of n, where n is the number of days after the initial observation. So, a few things going on here. Find the original infected population. Find the infected population after 3 days and 7 days. Draw the graph. Using the graph, estimate how long it will take for the infected population to reach 12,000. All right, let's start having a look at this question here. So, as I said before, the original infected population or the initial population, all right, occurs at t equals 0, all right, or in our case, n. So, for time's sake, we're going to use our n equals 0. So, what this means, P of 0 is equal to, grab our equation, 1,500 times by 1.25, all right, to the power of n, but n is 0, all right. So this is 1,500 times by 1, because anything to the power of 0 is 1, which is 1,500 people. Okay, so that is our initial infected population. All right, part B, all right, find the infected population after 3 days. All right, so instead of having n equals 0, we have n equals 3. So we are finding P of 3, so 1,500 times by 1.25 to the power of 3. Now, if you've got your calculator handy, you will see that that is approximately 2,929.69 people. But we obviously can't have 0.69 people, so we are going to round up because we need to incorporate that almost 2/3 of a person. So we have 2,930 people after 3 days. All right. So part 2 of B, so that was part 1. Part 2 of B was n equals 7. So after 7 days, so P of 7 is equal to 1,500 times by 1.25 to the power of 7. And we can find on our calculator that that is equal to approximately 7,152.56. All right, and again, rounding up, so we have 7,153 people infected after 1 week or 7 days. All right, part C is now graphing this equation. All right, so typically with our exponential equations, we don't look past into the negative of our x coordinate, so you will often be able to draw your graph looking like this. All right, so our initial, so let's do a scale. We've got 2, 6, 8, 10, 12, 14, 16, 18, that'll do. And what x equals 7 was 7,000, so it's going to grow quite a bit. So if we go up to 15,000, just like that. Let's have a look. Yep, that works. So we've got 5,000 and we've got 10,000 here. All right, so that's our scaling. So initial was 1,500 people. So if we're looking at our scale, that's going to be about there. All right. After 3 days, it was just under 3,000 people. All right, so that's going to be about here. All right. And then 7 days, 7,153 people. So that's going to be about here. So we can model this shooting up like that. All right. Now it looks a little bit cramped, but that's just how our exponential function is operating. So all we need to do now is put in our equation, 1,500 times by 1.25 to the power of n. All right, so y equals, or in terms of our population, p with respect to n. Okay, part D, using the graph, estimate how long it will take for the affected population to reach 12,000. So that's going up to about 12,000. Doing a nice dot across. So according to our graph, just past 11 days is when our population will reach 12,000. So we've got 11 days approximately. All right. So there's sort of the questions you're going to get, substituting in to find population or size after a certain amount of time, graphing, and using the graph to find answers to questions. Hopefully this helps a little bit. That was a growth example. Decay is exactly the same, except we'll have a decaying looking model. All right, we'll see you guys in the next video.